Scientists have finally done it. After decades of telling us it was impossible, researchers have unveiled a new method that could allow spacecraft to travel 10 times faster than light. This is not science fiction. This is not a distant dream. This is happening right now in laboratories and research centers around the world, where brilliant minds are rewriting everything we thought we knew about the speed limit of the universe. If you are finding comfort in these cosmic explorations, please consider giving this video a like and subscribing to our channel. Your support helps us continue bringing you these gentle journeys through the wonders of the universe. Tonight, as you settle into your bed and let the stars wash over you, we are going to take a journey together. A journey that begins with a rule that has governed our understanding of the cosmos for over a century. A rule that says nothing, absolutely nothing, can travel faster than light. And yet, as we drift deeper into this story, you will discover how scientists are finding ways around this cosmic speed limit, not by breaking the rules of physics, but by bending them in ways that Einstein himself might have appreciated. Let us begin at the beginning. Let us start with light itself and understand why it has been considered the ultimate speed limit of everything that exists. Picture yourself standing outside on a clear night. Look up at the sky. Those tiny points of light scattered across the darkness are stars, just like our own sun. But here is something remarkable to consider. The light entering your eyes right now, the light from those distant stars, has been traveling through the emptiness of space for years, sometimes for hundreds of years, sometimes for thousands. The light you see from the nearest star to our sun, a small red dwarf called Proxima Centauri, left that star over 4 years ago. It has been racing through the void at an almost unimaginable speed ever since, just to reach your eyes in this moment. Light travels at approximately 186,000 miles per second. That is about 300,000 kilometers per second. In the time it takes you to blink, light could circle the entire Earth more than 7 times. It is so fast that when you flip a light switch in your room, the light seems to fill the space instantly. There is no perceptible delay between the switch and the illumination, because light crosses that short distance in a time too brief for human senses to detect. And yet, despite this incredible speed, the universe is so vast that even light takes years to cross the distances between stars. Our galaxy, the Milky Way, is about 100,000 light years across. That means if you could somehow travel at the speed of light, it would still take you 100,000 years to cross from one side of our galaxy to the other. And our galaxy is just one of hundreds of billions of galaxies in the observable universe. This is the cosmic speed limit that has haunted scientists and dreamers alike since Albert Einstein first described it in his special theory of relativity in 1905. According to Einstein, nothing that has mass can ever reach the speed of light, let alone exceed it. The faster an object moves, the more energy it requires to go faster still. As that object approaches the speed of light, the amount of energy needed approaches infinity. You would need more energy than exists in the entire universe just to push a single grain of sand up to light speed. This was the wall, the barrier, the cosmic rule that seemed to lock humanity forever within a tiny bubble of space, unable to reach even the nearest stars within a human lifetime. But Einstein was a clever man, and in his later work, his general theory of relativity from 1915, he revealed something remarkable about the universe. He showed us that space and time are not separate, rigid things. They are woven together into a single fabric called spacetime, and this fabric can be bent, stretched, curved, and warped by the presence of mass and energy. Think of it like a trampoline. If you place a heavy bowling ball in the center of a trampoline, the fabric stretches and curves around it. If you then roll a marble across the trampoline, the marble will curve toward the bowling ball, not because there is any force pulling it, but because it is following the curved shape of the fabric itself. This is how gravity works according to Einstein. The sun does not reach out and pull the Earth toward it. Instead, the massive sun curves the fabric of space-time around it, and the Earth simply follows the curved path through that warped space. This insight would prove to be the key to unlocking faster than light travel, not by moving through space faster than light, but by manipulating the fabric of space itself. For decades after Einstein published his work, scientists explored the mathematics of general relativity. They discovered black holes, regions of space where the curvature becomes so extreme that not even light can escape. They discovered that the entire universe is expanding, with space itself stretching between the galaxies. And buried within these equations, some researchers began to notice something extraordinary. The expansion of the universe provides a hint of what is possible. Right now, at this very moment, galaxies at the far edges of the observable universe are moving away from us faster than light. This might sound like it violates Einstein's speed limit, but it does not. Those distant galaxies are not moving through space faster than light. Instead, the space between us and them is expanding. New space is being created, and that expansion can happen at any rate. There is no speed limit for the expansion of space itself. This is a crucial distinction. Einstein's special relativity tells us that nothing can move through space faster than light. But general relativity reveals that space itself can stretch, contract, and flow in ways that are not bound by this limit. The universe has been exploiting this loophole since the Big Bang. And now, scientists are figuring out how we might exploit it too. The story of the modern warp drive begins in an unexpected place. It begins in a student dormitory at the University of Cardiff in Wales in the early 1990s. A young Mexican physicist named Miguel Alcubierre was pursuing his doctorate in numerical relativity, learning how to use powerful computers to solve Einstein's complex equations. Like many students, he needed breaks from his demanding studies. And like many people in the early 1990s, he found relaxation in television. Every Friday night, Alcubierre and his friends would gather to watch Star Trek: The Next Generation. They would rent VHS tapes of the latest episodes and immerse themselves in the adventures of Captain Picard and the crew of the USS Enterprise. In Star Trek, the Enterprise could travel between star systems in days or weeks thanks to its warp drive. The ship would engage its engines, space would seem to stretch and blur on the view screen, and moments later they would arrive at a distant star system that would have taken thousands of years to reach using conventional rockets. Most people watching Star Trek simply accepted the warp drive as science fiction, a convenient plot device that made interstellar adventure possible. But Alcubierre was different. He was a physicist. He spent his days working with Einstein's equations, manipulating the mathematics of curved space-time. And one night, watching the Enterprise streak across the galaxy, a thought occurred to him. What if the warp drive was not just fiction? What if there was a way to make it real? The idea kept him awake that night. He could not shake it from his mind. The next day, he went to his office and began doing calculations. What he found astonished him. By carefully specifying the shape of a particular space-time curvature, Alcubierre discovered that he could create what he called a warp bubble. Inside this bubble, a spacecraft would sit in a region of perfectly flat, undisturbed space. The ship would not be moving at all relative to its local surroundings, but the bubble itself and everything inside it would be carried along by the deformation of spacetime around it. In front of the bubble, space would contract, shrinking down like an accordion being squeezed. Behind the bubble, space would expand, stretching out. The net effect would be like riding a wave on the ocean. The ship is not moving through the water, the wave is carrying it along. And just as there is no speed limit for ocean waves, there is no speed limit for the expansion and contraction of spacetime. Alcubierre's calculations showed that, at least mathematically, a spacecraft enclosed in such a bubble could travel at arbitrarily fast speeds, 10 times the speed of light, 100 times, 1,000 times. The mathematics did not care. As long as the bubble maintained its shape, the passengers inside would experience no acceleration, no crushing g-forces, no time dilation effects. They would simply sit comfortably, in flat space, while the universe slid past them at fantastic velocities. In 1994, Alcubierre published his paper in the prestigious journal Classical and Quantum Gravity. The paper was titled The Warp Drive, Hyperfast Travel Within General Relativity. It caused a sensation in the physics community. Here was a respected scientist showing that faster-than-light travel was not prohibited by Einstein's equations. It was actually predicted by them under the right circumstances. But there was a catch. A very big catch. To create the warp bubble that Alcubierre described, you would need a special kind of matter. Not ordinary matter like atoms and molecules. Not even the exotic particles that physicists create in their massive accelerators. You would need something called negative energy matter. This hypothetical substance would have properties that are essentially the opposite of normal matter. Where normal matter creates gravity that pulls things together, negative energy matter would create a kind of anti-gravity that pushes things apart. The problem is that negative energy matter has never been observed. We have no idea how to create it. Some physicists believe it might be fundamentally impossible to produce in the quantities needed for a warp drive. The original Alcubierre drive would require negative energy equivalent to the mass of an entire planet, or perhaps much more. Some calculations suggested you would need more energy than exists in the entire observable universe. This was the stumbling block that stopped the warp drive from being anything more than an interesting mathematical curiosity. Yes, Einstein's equations allowed for this kind of space-time manipulation, but the ingredients required to actually build such a thing seemed impossibly out of reach. For 30 years, the Alcubierre drive remained in this frustrating state. Possible in theory, impossible in practice. Scientists wrote papers refining the mathematics, exploring the implications, and finding ways to reduce the energy requirements. But the fundamental problem remained. You needed exotic negative energy, and we had no way to get it, until now. In early 2024, a team of physicists did something remarkable. They found a way to create a warp drive model that does not require negative energy at all. This is the breakthrough that has changed everything. The research came from a collaboration between scientists at the University of Alabama in Huntsville and a research organization called Applied Physics, based in New York. The lead author was a physicist named Jared Fuchs, working alongside Christopher Helmerich and a team of dedicated researchers. They had been working for years on this problem, developing sophisticated computer programs to analyze warp drive spacetimes. What they discovered was a way to create a warp bubble using only positive energy. Positive energy is the kind of energy we deal with every day. It is light, heat, matter, antimatter. It is the stuff that actually exists in our universe, not hypothetical exotic matter that may or may not be possible. The key to their breakthrough was rethinking how the warp effect actually works. For years, scientists had assumed that a warp drive required space to expand behind the ship and contract in front of it. But Fuchs and his team showed that this is not quite right. The warp effect does not actually come from expanding or contracting space. It comes from having large amounts of energy moving rapidly around the passenger volume. Think of it like a smoke ring. When you blow a smoke ring, the air particles move in a circular pattern that creates a stable, moving structure. The smoke ring can drift across a room, carrying itself along through the air. The warp bubble works similarly. Large amounts of energy circulating around the ship create a conveyor belt effect that can transport the entire bubble through spacetime. By arranging positive energy in the right configuration, moving in the right patterns around a hollow interior, the team showed that you can create genuine warp effects. The passengers inside would feel no acceleration. There would be no crushing forces. Clocks inside the bubble would stay synchronized with clocks on Earth. It would be, in the words of the researchers, quite ideal for human travel. There is still a catch, of course. The amount of positive energy required is enormous. The current models would need energy equivalent to the mass of 2 Jupiter-sized planets. We cannot produce that much energy yet, but here is the crucial difference. We know positive energy exists. We know how to work with it. It is not forbidden by the laws of physics. It is simply an engineering problem, albeit an extremely difficult one. And the team has shown that the energy requirements depend strongly on the shape of the warp bubble. Flatter bubbles require less energy. Different configurations have different demands. With further refinement, the energy requirements might be reduced to more manageable levels. This study changes the conversation about warp drives, Fuchs said, when announcing the results. By demonstrating a first-of-its-kind model, we have shown that warp drives might not be relegated to science fiction. But the breakthroughs did not stop there. In December of 2025, just weeks ago, another major advance was announced. A team led by Harold Sonny White, a former NASA scientist who spent years working on advanced propulsion concepts at the Johnson Space Center, published a new paper in the journal Classical and Quantum Gravity. White had been chipping away at the warp drive problem for decades, and his latest work proposed a fundamentally new approach to the geometry of warp bubbles. The original Alcubierre drive imagined the warp bubble as a smooth, continuous ring of energy surrounding the spacecraft. White asked a simple but profound question. What if you broke that ring into separate pieces? Instead of a single continuous ring, White proposed using multiple cylindrical structures arranged around the ship. He called them nacelles, a term that Star Trek fans will immediately recognize. In the fictional Star Trek universe, the nacelles are the distinctive cylindrical engine pods that extend from the main body of the Enterprise. White showed that these familiar shapes are not just science fiction. Aesthetics. They might actually reflect the optimal geometry for a real warp drive. By separating the warp energy into distinct cylindrical pods, the mathematics becomes more manageable. The dangerous forces and exotic energy requirements can be confined to the nacelle regions, keeping the interior of the ship flat, calm, and safe for passengers. The design allows for modular, engine-like structures rather than a single unmanageable energy field. White explained that this new geometry allows for structures that act as modular propulsion units. The resemblance to the twin nacelles of the USS Enterprise is not merely aesthetic, but reflects a potential convergence between physical requirements and engineering design. Science fiction architectures, it seems, hint at practical pathways for real warp-capable configurations. The paper was groundbreaking enough. that Miguel Alcubierre himself, the physicist who started this entire field of research back in 1994, endorsed the new model. Having the original warp drive theorist validate your work is like having Einstein himself show up to your physics class. So where does this leave us? Can we actually build a warp drive and travel to the stars? The honest answer is that we are still far from having a working prototype. These are mathematical models and theoretical frameworks. We cannot yet produce the enormous amounts of energy required, even with positive energy. We do not have the materials or technology to shape that energy into the precise configurations needed for a stable warp bubble. But here is what has changed. We now know that warp drives are not forbidden by physics. We know that they do not require impossible exotic matter. We have mathematical blueprints that obey the laws of general relativity. We have multiple teams around the world working on refining these models, reducing energy requirements, and exploring different configurations. One team at Applied Physics has even created software called Warp Factory that allows researchers to model different warp drive designs and analyze their properties. The software is publicly available. Anyone can download it and experiment with their own ideas. This kind of open collaboration is accelerating the pace of discovery. The researchers involved in this work are careful to temper expectations. While we are not yet packing for interstellar voyages, explained Gianni Martir, CEO of Applied Physics, this achievement heralds a new era of possibilities. We are continuing to make steady progress as humanity embarks on the warp age. And what an age it could be. Let us dream for a moment. Let us imagine a future where warp drives become reality. What would it mean for humanity? Consider our nearest stellar neighbor, Proxima Centauri. This small red dwarf star lies about 4.2 light-years from Earth. That means light itself, traveling at 186,000 miles per second, takes over 4 years to make the journey. With our current fastest spacecraft, the Voyager probes traveling at about 38,000 miles per hour. It would take over 70,000 years to reach Proxima Centauri. 70,000 years. Our entire recorded human history spans only about 6,000 years. But with a warp drive capable of traveling at 10 times the speed of light, we could reach Proxima Centauri in less than 6 months. And there is something waiting for us there that makes this journey particularly exciting. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri. They called it Proxima Centauri b, and it is remarkable. This world orbits in the habitable zone of its star, the region where temperatures might allow liquid water to exist on the surface. It is roughly Earth-sized, with a mass about 1.3 times that of our planet. It could be rocky with a solid surface. It could have an atmosphere. It could potentially harbor life. We have found what might be another Earth, right next door in cosmic terms. But with our current technology, we have no way to visit it. We can only look at it from afar, 4 light-years away, wondering what secrets it holds. A working warp drive would change everything. Imagine launching a mission to Proxima Centauri b. A spacecraft equipped with a warp drive departs Earth orbit, engages its engines, and creates a bubble of warped space-time around itself. Inside the bubble, the crew feels nothing unusual. They float in comfortable microgravity, going about their daily routines. But outside their ship, space is contracting ahead of them and expanding behind them. The stars on their view screen shift and blur as the fabric of space-time carries them forward. Months later, the warp bubble dissipates, and they find themselves in orbit around an alien star. A small red sun hangs in the sky, cooler and dimmer than our yellow sun. Below them, a world turns slowly in that ruddy light. Clouds drift across continents. Oceans glint with reflected starlight. And for the first time in human history, people from Earth are looking down at another planet around another star. They descend to the surface in a landing craft. The air might be breathable. The gravity would be familiar. They step out onto alien soil and become the first humans to walk on a world beyond our solar system. This is what warp drives make possible. Not just faster travel, but a fundamental transformation of humanity's relationship with the cosmos. We would no longer be trapped on a single world, hoping that asteroid strikes or supervolcanoes do not end our species. We would have the entire galaxy available to us. And the galaxy is vast beyond imagination. Our Milky Way contains somewhere between 100 billion and 400 billion stars. That is more stars than there are grains of sand on all the alone in the universe is perhaps the most profound question humanity has ever asked. And the answer lies scattered across the light years of our galaxy. To find it, we need to go there. We need to see these worlds up close. We need to analyze their atmospheres, sample their soils, and search for the signs of life or civilization. Warp drives would give us the keys to this cosmic treasure hunt. But let us bring ourselves back to the present moment. Let us settle more deeply into our beds and consider the journey that has brought us to this point. The story of warp drives is really the story of human imagination meeting mathematical reality. It began with fiction, with stories of starships and alien encounters. It continued with physics, with Einstein's revolutionary insights into the nature of space and time. And now it progresses with engineering, with practical-minded scientists working out the details of how these fantastic machines might actually be built. There is a beautiful symmetry to this process. Fiction inspires science. Science enables engineering. Engineering creates new realities that inspire new fiction. The cycle continues, each generation standing on the shoulders of those who came before, reaching ever higher toward the stars. Albert Einstein himself appreciated this connection between imagination and discovery. Imagination is more important than knowledge, he once said. For knowledge is limited to all we now know and understand, while imagination embraces the entire world and all there ever will be to know and understand. Miguel Alcubierre imagined a warp drive while watching Star Trek. That imagination led him to discover something real hidden within Einstein's equations. Harold Sonny White imagined breaking the warp ring into nacelles, and that imagination led to a more practical geometry. Jared Fuchs and his team imagined a warp drive without exotic matter, and that imagination led to a breakthrough that uses only positive energy. Each step forward begins with someone daring to imagine that the impossible might actually be possible. And this is the essence of what makes humanity remarkable. We are not content to accept limits. We are not satisfied to stay in one place, to know only what we already know, to see only what we can see from where we stand. We are a species of explorers, dreamers, and builders. We crossed oceans on wooden ships. We conquered the sky with aluminum wings. We walked on the moon with suits of fabric and metal. And now we are reaching for the stars with equations and energy. The universe is not a hostile place. It is indifferent. It does not care whether we explore it or stay home. It will not congratulate us if we succeed or mourn us if we fail. But it is full of wonders waiting to be discovered, mysteries waiting to be solved, beauty waiting to be witnessed. Consider what else awaits us out there in the cosmos. The nearest large galaxy to our Milky Way is the Andromeda Galaxy, about 2.5 million light-years away. With a warp drive capable of 10 times light speed, the journey would still take 250,000 years. That sounds like a long time, and it is. But compare it to what we face without warp drives. At the speed of Voyager 1, reaching Andromeda would take roughly 45 billion years. That is more than 3 times the current age of the universe. With warp drives, at least the journey becomes finite, conceivable, perhaps achievable, if we continue to improve the technology. And between here and Andromeda, there are countless wonders to explore. There are star systems with multiple suns, where alien worlds might experience sunrises in 3 colors. There are neutron stars, the collapsed cores of dead giants, spinning hundreds of times per second and emitting beams of radiation like cosmic lighthouses. There are stellar nurseries, vast clouds of gas and dust, where new stars are being born even now, their light not yet switched on. There are planetary systems utterly unlike our own, with giant worlds orbiting where Mercury should be, and ice worlds drifting in the far darkness. And there are black holes. These cosmic oddities deserve their own moment of contemplation. Tonight, black holes are regions of spacetime where gravity has become so intense that nothing, not even light, can escape once it crosses the boundary called the event horizon. They are the ultimate destinations for matter and energy, one-way doors into the unknown. Some black holes are small, just a few times the mass of our Sun, formed when massive stars collapse at the end of their lives. Others are supermassive, containing millions or billions of solar masses, lurking at the centers of galaxies including our own. The black hole at the heart of the Milky Way is called Sagittarius, a star. It has a mass of about 4 million suns, and it is relatively quiet now, sleeping in the galactic core. With warp drives, we could visit these cosmic monsters. We could study them up close, observing how they bend light and distort space-time in their immediate vicinity. We could drop probes past their event horizons and learn what happens in those regions where our current physics breaks down. We could answer questions about the nature of gravity, the structure of space-time, and perhaps the ultimate fate of information that falls into these cosmic sinkholes. And there may be practical reasons to visit black holes as well. Some theorists have suggested that the intense gravitational fields near black holes could be harnessed for energy. Others have speculated about using black holes as anchors for wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe. These ideas remain highly speculative. But then again, so did warp drives just a few years ago. The pace of discovery is accelerating. What seems impossible today might be engineering homework tomorrow. Let us drift now into a deeper contemplation of time and space. The warp drive discussions often focus on speed, on how fast we could travel between the stars. But there is another aspect to this technology that is equally profound. When you travel at close to the speed of light using conventional propulsion, time behaves strangely. Einstein's special relativity tells us that moving clocks run slow. If you got in a rocket and traveled to a nearby star at 90% of the speed of light, you would experience the journey as taking far less time than an observer on Earth would measure. You might age 5 years during the trip, while your friends back on Earth age decades. This effect, called time dilation, has been verified experimentally countless times. It is not a theory, it is an observed fact of the universe. Astronauts on the International Space Station, traveling at just 17,000 miles per hour, age slightly less than people on the surface of Earth. The effect is tiny at such slow speeds, but it is measurable. For interstellar travel using conventional rockets, time dilation would be significant. it creates a painful dilemma for would-be explorers. You could journey to the stars and return, but everyone you ever knew would be long dead. You would be a stranger in a future world, displaced not just in space but in time. Warp drives elegantly solve this problem. Inside a warp bubble, time flows normally. The passengers are not moving through space. They are riding a wave of contracted and expanded space-time. There is no relative velocity in the usual sense, so there is no time dilation. Clocks inside the warp bubble stay synchronized with clocks on Earth. A trip to Proxima Centauri that takes 6 months. Ship time also takes 6 months Earth time. When you return home, your friends will have aged the same amount as you. This might seem like a small detail, but it transforms interstellar travel from a one-way exile into a real, round-trip journey. Explorers could leave Earth, visit distant star systems, conduct their research, and return home to share their discoveries with the same generation that sent them out. Families would not be torn apart by centuries of separation. Human civilization could expand across the galaxy while remaining connected as a single society. This is the vision that warp drive researchers are working toward. Not just faster spaceships, but a new era of cosmic civilization. A future where the light years that separate the stars are no longer an insurmountable barrier, but merely an interesting engineering challenge. Of course, building actual warp drives will require solving many problems that we have not yet discussed. Energy is the most obvious challenge. Even the most optimistic current models require energy equivalent to the mass of planets. We do not have any power source that can produce such quantities. Our most powerful nuclear reactors generate trivial amounts of energy compared to what is needed. Even controlled fusion, if we ever achieve it, would fall far short of warp drive requirements. One possibility is antimatter. When matter and antimatter meet, they annihilate each other completely, converting their entire mass into pure energy according to Einstein's famous equation E equals mc squared. A single gram of antimatter meeting a gram of matter would release an explosion equivalent to about 43 kilotons of TNT, nearly 3 times the power of the Hiroshima bomb. Antimatter is the most efficient fuel conceivable within known physics, but we cannot produce antimatter in useful quantities. The world's particle accelerators create tiny amounts of antiparticles in high-energy collisions, but capturing and storing them is extraordinarily difficult. It has been estimated that all the antimatter ever produced by humanity would not boil a cup of water. Scaling this up to warp drive quantities would require revolutionary advances in physics and engineering. Another challenge is the materials needed to construct a warp drive. The engines would need to precisely shape and control enormous amounts of energy in specific configurations. They would need to create and maintain a stable warp bubble while protecting the passengers inside. They would need to survive the extreme conditions near the edges of the bubble, where space-time curvature becomes intense. We have no materials that could withstand these conditions. We have no experience building structures that manipulate space-time directly. Even understanding what such materials and structures would need to be like requires advances in physics that we have not yet made. And then there are the safety considerations. A warp drive would be the most powerful machine ever constructed by humanity. Even small malfunctions could have catastrophic consequences. What happens if the warp bubble collapses while the ship is in transit? What happens if the bubble destabilizes near a planet? How do you navigate while inside a bubble of warped space-time, unable to receive signals from the outside world? These are not trivial concerns. They are fundamental challenges that will require decades or centuries of careful work to address. but humanity has faced impossible challenges before. Consider the history of flight. In 1903, the Wright brothers flew their fragile wooden aircraft for 12 seconds, covering 120 feet. Most people thought heavier than air flight was impossible. Yet just 66 years later, in 1969, astronauts were walking on the moon. The same human lifetime that began with the first wobbly airplane flights ended with footprints in lunar dust. The first computers filled entire rooms and could barely perform basic calculations. Now we carry devices in our pockets that are millions of times more powerful. The first vaccines were crude, dangerous, and barely effective. Now we can sequence a new pathogen's genome and develop a vaccine against it within months. Progress is not linear, it accelerates. Each discovery enables the next. Each breakthrough opens new possibilities that were previously unimaginable. The warp drive researchers understand this. They are laying the foundations for a technology that they know will not be completed in their lifetimes. But they are doing the work anyway. They are solving the mathematical problems, developing the computational tools, publishing the papers that will guide future generations. As Gianni Martir put it, they can see the light at the end of the tunnel. The path is long and difficult, but it is no longer invisible. And so we find ourselves at a remarkable moment in human history. For the first time, we can seriously contemplate becoming an interstellar species, not through generations ships that would take thousands of years to reach other stars, not through frozen colonists who would never see Earth again, but through practical, survivable, round-trip journeys that would transform our relationship with the cosmos. This is what the latest warp drive research represents. It is not just an interesting physics puzzle. It is the blueprint for humanity's future among the stars. Let us now drift into the deeper cosmic perspective. Let us zoom out from our blue planet and consider our place in the universe. We live on a small rocky world orbiting an ordinary yellow star in the suburbs of an ordinary spiral galaxy. Our Sun is one of perhaps 400 billion stars in the Milky Way. The Milky Way is one of perhaps 200 billion galaxies in the observable universe. The observable universe is 93 billion light-years across, and it may be just a tiny fraction of the total universe, which could be infinite. On this scale, humanity's current reach is almost immeasurably small. Our radio signals, traveling at the speed of light since we first started broadcasting, have covered only a tiny bubble of space a few hundred light-years across. That is less than 1% of 1% of our own galaxy. The universe beyond is utterly unaware of our existence. Some people find this perspective humbling to the point of despair. What does anything matter, they ask, if we are so small and the universe is so vast? What significance can our lives have in the face of such cosmic indifference? But there is another way to look at it, a way that the warp drive researchers seem to have embraced. The universe is vast, yes, but it is also full of possibility. Every light year of space contains wonders we have not yet seen. Every star system holds potential discoveries that could transform our understanding. Every planet might be a new chapter in the story of life, of intelligence, of consciousness exploring itself through material forms. We are not small. We are the universe becoming conscious of itself. Through us, through our instruments and equations and daring expeditions, the cosmos is waking up. It is looking at itself. It is asking questions about its own nature and origin. The warp drive researchers are part of this awakening. They are working to give the universe eyes that can see across light years, hands that can reach other stars, a presence that can spread and flourish among the countless worlds that await. This is the grand project of intelligence. Not just survival, though that matters. Not just prosperity, though that matters too. But exploration, discovery, understanding. The transformation of blind matter into seeing, knowing, wondering mind. The stars call to us because we are made of their dust. The atoms in your body, the carbon and oxygen and iron that make up your flesh and blood, were forged in the hearts of stars that burned and died billions of years ago. You are quite literally star stuff, as the astronomer Carl Sagan loved to remind us. And now that star stuff has organized itself into patterns complex enough to wonder about its origins, to dream of returning to the stars from which it came. This is not poetry, this is physics. The warp drive equations, the space-time geometries, the energy requirements, all of this technical work is in service of a deep truth about who we are and where we belong. We belong to the universe, all of it. And one day, thanks to the work being done right now, we may finally claim that inheritance. As your eyes grow heavy and sleep approaches, let us take one last journey through the cosmos. A journey that begins here tonight, in this room where you rest, and extends outward to the very edges of what we can see. Start with Earth beneath you, this beautiful blue marble swirled with white clouds and brown continents, the only home humanity has ever known. Feel the weight of your body pressing into the bed, gravity pulling you gently toward the planet's core. This is the force that Einstein taught us is not really a force at all, but the curvature of space-time created by Earth's mass. Now rise up in imagination, float above the clouds, above the atmosphere, into the blackness of space. Look back at Earth, a precious jewel, glowing in the sunlight. From here, you can see no borders, no nations, no divisions, just a single world, impossibly fragile, impossibly beautiful. Turn away and look toward the moon. That pale circle has watched over Earth for over 4 billion years. Humans have walked there, left footprints that will last for millions of years in the airless vacuum. The moon is about 240,000 miles away. Light reaches it in just over a second. Now travel outward, past the moon, toward the inner planets. Mercury, closest to the sun, a scorched and cratered world. Venus, shrouded in thick clouds of sulfuric acid, its surface hotter than an oven. Mars, the red planet, with its ancient riverbeds and towering volcanoes, a world that might one day host human colonies. The asteroid belt comes next, a vast ring of rocky debris left over from the formation of the solar system. Then the gas giants. Jupiter, king of planets, its great red spot, a storm larger than Earth that has raged for centuries. Saturn, ringed in glory, its frozen moons potentially harboring liquid water oceans beneath their icy shells. Uranus and Neptune, ice giants in the outer darkness, barely touched by the sun's distant warmth. Beyond Neptune lies the Kuiper Belt, a region of icy bodies including Pluto, once called the 9th planet, and beyond that, the Oort cloud, a vast sphere of primordial comets extending perhaps 2 light years from the sun. This is the outer boundary of our solar system, the edge of our star's gravitational influence. We have reached this far with our robot emissaries. Voyager 1 and 2, launched in 1977, are now in interstellar space, carrying golden records that tell the story of Earth to any beings who might find them. But they are moving so slowly by cosmic standards, it will take them tens of thousands of years to approach other stars. Now make the leap. Point yourself toward Proxima Centauri, that nearest star. Imagine engaging a warp drive, feeling the universe compress before you and expand behind you. In your mind, you are making the journey that scientists are working to make possible. Proxima Centauri grows brighter ahead. A small red star, cooler and dimmer than our Sun, but ancient and stable. Its planet, Proxima b, comes into view. Is there life there? Are there oceans and continents, forests and creatures? Or is it a barren rock, interesting only to geologists? We do not know yet, but we might find out someday, thanks to warp drives. Turn now and look back. From here, 4.2 light-years away, the Sun is just another star in the sky. A bright one, certainly, but not obviously special. Earth is invisible, lost in the glare. Everything you have ever known, everyone you have ever loved, exists around that tiny point of light. This is the view that future explorers might see. They will look back at their distant home and marvel at how far they have come. They will feel both the vastness of the universe and the preciousness of their origins. Continue outward in imagination. Pass other stars, other systems. Some have planets of their own. Some might have life. Some might have intelligence. The galaxy spreads around you, a great wheel of light containing hundreds of billions of stars. From the outside, looking at the Milky Way, it would appear as a graceful spiral, arms of stars and gas curling around a bright central core. Our Sun is located about 2/3 of the way out from the center, in a relatively quiet neighborhood between spiral arms. Keep going. Leave the Milky Way behind. Watch it shrink to a smear of light, then a point, then disappear among countless other galaxies. The Andromeda galaxy swings past, larger than the Milky Way, but similar in structure. The local group of galaxies, our cosmic neighborhood, contains dozens of members. Beyond the local group, galaxy clusters stretch across the universe, great walls and filaments of matter, separated by vast voids of nearly empty space. The structure of the cosmos on the largest scales resembles a foam, with galaxies concentrated along the bubble surfaces and emptiness within, at the edge of the E-Algae observable universe, nearly 46 billion light-years in every direction. Light from the cosmic microwave background reaches us. This is the oldest light in the universe, released when the cosmos was just 380,000 years old and first became transparent. Beyond this, we cannot see, not because there is nothing there, but because light from more distant regions has not had time to reach us yet. This is the universe that awaits exploration. This is what warp drives could help us access. Not all of it, perhaps. The universe may be infinite, and no technology could let us see it all, but enough of it to keep humanity exploring for millions of years. Enough to answer questions we have not yet thought to ask. Enough to transform us into something we cannot yet imagine. As sleep claims you now, carry this vision with you into your dreams. The stars are not unreachable. The distances between them are not infinite. The speed of light is a limit, yes, but it is a limit that can be circumvented, not by breaking the rules, but by understanding them deeply enough to work around them. Scientists are doing that work right now, in universities and research institutes around the world. Brilliant minds are pushing the boundaries of what is possible. They are writing the equations that future engineers will turn into blueprints. They are dreaming the dreams that future builders will make real. And you, listening to these words as you drift toward sleep, are part of this story. You are a being made of star stuff, contemplating the stars from which you came. You are consciousness become curious about its own origins and possibilities. You are humanity's wonder at the universe, given form and awareness. The journey to the stars begins here, tonight, with this knowledge settling into your mind. The universe is vast but not hostile. The distances are great but not infinite. The challenges are immense but not impossible. One day, perhaps, your descendants will stand on alien worlds and look up at unfamiliar constellations. They will remember the generations that came before, the dreamers and scientists and engineers who made their presence there possible. They will remember that it began with people like you, wondering at the stars and daring to imagine reaching them. Until that day comes, rest well. Let the cosmos cradle you in its vast and patient embrace. The stars will still be there when you wake, shining their ancient light across the void, calling to all who would explore their mysteries. Sleep now, knowing that the universe is more accessible than we once believed. Sleep knowing that faster than light travel, once thought impossible, is now understood to be permitted by the very equations that govern reality. Sleep knowing that humanity is on the path to the stars, one breakthrough at a time. The warp drive awaits. The cosmos awaits. And the greatest adventure in human history is just beginning. Drift peacefully through your dreams tonight. Let them carry you to distant stars and alien worlds. Let them show you civilizations we have not yet met and wonders we have not yet witnessed. For in dreams, as in physics, the impossible sometimes becomes possible, and what we imagine today, we may achieve tomorrow. The universe is calling, and thanks to the work of scientists like Alcubierre, Fuchs, White, and countless others, we are learning how to answer. Good night, fellow traveler. May your journey through sleep be as wondrous as the journey through space that awaits humanity. The stars are waiting, and one day we will meet them. In the quiet darkness of your room, as your breathing slows and your thoughts begin to fade, remember this: you are made of stars, contemplating stars, dreaming of stars. And that dream is slowly, steadily, inevitably becoming reality. Rest now. The universe will still be there in the morning, vast and mysterious and beautiful, and the work of reaching it will continue, one equation at a time, one breakthrough at a time, one dream at a time. Good night. As you continue to settle deeper into rest, let us linger a while longer on the remarkable nature of this moment. For we stand at a pivot point in cosmic history, a threshold between what was and what might be. For almost the entire existence of our species, roughly 300,000 years, humans have looked up at the night sky and wondered. We watched the stars wheel overhead through the seasons. We gave them names and stories. We used them to navigate across oceans and deserts. But we always knew, on some level, that they were impossibly far away. They were lights in the sky, beautiful but untouchable. Even as our understanding grew, even as we learned that the stars were other suns, and that those suns might have worlds of their own, the distances remained overwhelming. The more we learned about the universe, the more impossibly vast it seemed. Each new discovery pushed the boundaries further outward. Our galaxy contained billions of stars. The universe contained billions of galaxies, and between all of them stretched light years upon light years of empty space. For much of the 20th century, this vastness was a source of melancholy for those who dreamed of space exploration. Even science fiction authors, who regularly invented faster than light travel for their stories, often acknowledged that they were cheating. They were ignoring the physics to tell their tales. Real space travel, everyone assumed, would always be slow and difficult, limited by Einstein's speed limit to journeys that would take generations. But now, in the early decades of the 21st century, that assumption is being challenged. The mathematics of general relativity, the same equations that establish the speed of light as a barrier, are revealing loopholes, paths through the equations that allow for the impossible, ways to manipulate spacetime itself that could carry spacecraft at speeds that would have seemed magical just decades ago. This is what makes the current moment so extraordinary. We are not merely dreaming about the stars anymore. We are calculating, we are modeling. We are publishing peer-reviewed papers in prestigious journals, having them endorsed by the very physicists who opened this field of research. We are building the intellectual infrastructure for interstellar travel. The transition from dream to engineering has begun. Consider the tools that warp drive researchers now have at their disposal. The Warp Factory software developed by the Applied Physics team allows scientists to model different warp drive geometries and calculate their energy requirements. This is not a toy or a video game. It is a serious computational tool based on the mathematics of general relativity, available for free to any researcher who wants to use it. Teams around the world are using these tools to explore the design space of possible warp drives. They are finding that the energy requirements depend strongly on the shape of the bubble, the configuration of the energy flows, the specific geometry of the warped spacetime. Flatter bubbles require less energy. Certain configurations are more stable than others. The design space is vast and largely unexplored, full of possibilities we have not yet discovered. This is how engineering projects begin, not with final blueprints for a working device, but with the gradual mapping of possibility space. The Wright brothers did not build a 747. They built a rickety wooden glider that barely flew. But in doing so, they demonstrated that heavier than air flight was possible. Everything else followed from that initial demonstration. The warp drive researchers are at a similar stage. They are demonstrating that faster than light travel is not forbidden by physics. They are mapping the mathematical territory, identifying the challenges, and exploring the solutions. The actual construction of a warp drive may be decades or centuries away, but the foundational work is happening now. And there are reasons to believe that progress might accelerate in unexpected ways. Throughout history, many technologies have progressed much faster than experts predicted. Nuclear energy went from theoretical concept to working reactor in less than a decade. The first computer that took up an entire room was followed just 40 years later by personal computers that fit on a desk. The Wright brothers flew in 1903. Humans walked on the moon in 1969. Again and again, the timeline from impossible to routine has been shorter than pessimists expected. There are several factors that could accelerate warp drive research. Advances in computational power are making it possible to model ever more complex spacetime geometries. Artificial intelligence systems might be able to explore the design space faster than human researchers alone. International collaboration is bringing together experts from different fields and different countries. And perhaps most importantly, the dream of interstellar travel is inspiring a new generation of physicists and engineers to devote their careers to making it possible. The warp age, as the Applied Physics team calls it, has begun. It may be in its earlier stages, equivalent to the first hesitant experiments with electricity or flight, but it has begun. And once a technological trajectory begins, it tends to continue until the goal is reached or proven truly impossible. As we drift deeper into the night, let us consider some of the specific challenges that remain and how they might be addressed. Energy remains the central obstacle. Even the most optimistic current models require energy equivalent to planetary masses. This is far beyond anything we can currently produce. But there are reasons to be hopeful. First, the energy requirements have been steadily decreasing as researchers refine their models. The original Alcubierre drive was estimated to need energy equivalent to the mass of the entire observable universe. Later refinements reduced this to the mass of Jupiter, The latest models have brought it down further. There is no guarantee that this trend will continue, but neither is there any proof that we have found the optimal configuration. More efficient designs may yet be discovered. Second, our understanding of energy is still evolving. A century ago, no one knew that matter and energy were equivalent, that E equals mc squared. 50 years ago, we were just beginning to understand the quantum vacuum, the strange energy that permeates all of space. Who knows what discoveries await us in the coming decades? Some breakthrough in physics, perhaps related to dark energy or quantum gravity, might reveal new sources of power that we cannot currently imagine. Third, even if the energy requirements remain enormous, that does not necessarily make warp drives impossible. It makes them expensive. But humanity has accomplished expensive things before when the motivation was strong enough. We built pyramids and cathedrals. We constructed a global network of satellites. We assembled a space station in orbit. With sufficient resources and determination, we can do remarkable things. The material challenges are similarly daunting, but not necessarily insurmountable. We need materials that can shape and contain enormous energies. We need structures that can survive the intense curvature at the edges of warp bubbles. We need systems that can create and maintain stable configurations of space-time. None of these requirements are beyond the scope of plausible future technology. We are already developing materials with extraordinary properties, nanotube structures, and metamaterials that behave in ways once thought impossible. We are learning to manipulate matter at the atomic scale. We are creating computational systems that can manage complexity far beyond human cognitive limits. The path from here to a working warp drive is not visible in detail, but we can see enough to know that it is not blocked by any fundamental barrier. It is hidden in the fog of the future, waiting to be discovered step by step. And in that fog, other possibilities shimmer. Warp drives are not the only way that general relativity might enable faster than light travel. Wormholes, theoretical tunnels through space-time that connect distant regions, have been studied for decades. Like warp drives, they require exotic matter to stabilize them. But like warp drives, new approaches might someday find ways around this requirement. There are also speculations about higher dimensions. String theory and related frameworks suggest that our familiar 3 dimensions of space might be embedded in a larger dimensional structure. If so, there might be ways to take shortcuts through these extra dimensions, effectively traveling faster than light without violating the speed limit within ordinary space. These ideas remain more speculative than warp drives. They have not yet reached the stage of serious engineering proposals, but they remind us that the universe is deeper and stranger than we often assume. The physics we know is powerful, but it is not complete. Future discoveries might open pathways we cannot currently envision. For now, the warp drive represents our best hope for interstellar travel. It is the approach that has received the most rigorous mathematical treatment. It is the concept that has progressed furthest toward practical engineering. And it is the technology that recent breakthroughs have brought tantalizingly closer to reality. As your thoughts begin to soften and blur toward sleep, hold on to the wonder of this moment. You are alive at a time when the stars are becoming accessible. You are witnessing the first steps of a journey that could carry your species across the galaxy. You are part of the generation that bridges the gap between earthbound past and spacefaring future. What a remarkable time to be conscious. What a gift to witness this unfolding. The cosmos has been patient. For billions of years it has waited in silence, its countless worlds orbiting its countless stars, its mysteries undiscovered, its wonders unseen. But now, on one small planet around one ordinary star, beings have arisen who can comprehend its structure, who can deduce its laws, who can dream of exploring its expanse. And those beings, those curious, dreaming, calculating beings, have just figured out that the distance between the stars is not the barrier it seemed to be, that space-time itself can be manipulated, that the universe, for all its vastness, might actually be accessible to minds bold enough to reach for it. This is the story of warp drives. This is why the latest research matters, not just as physics, though the physics is fascinating, not just as engineering, though the engineering is revolutionary, but as the opening chapter of a new era in the human story. The stars are calling, and we are learning to answer. Sleep now, gentle traveler. Let these thoughts accompany you into dreams. Let the vastness of the cosmos surround you like a blanket, warm despite its cold emptiness, comforting despite its immense distances. You are not small. You are the universe awakening. You are the stars becoming conscious. You are matter and energy, arranged into patterns that can contemplate their own nature and origin. And the future of your species among the stars, is brighter tonight than it has ever been. Rest well, dream deeply, and know that when you wake, the scientists will still be working. The equations will still be yielding their secrets. The path to the stars will still be unfolding. One day, perhaps sooner than anyone expects, the first warp bubble will form around the first interstellar spacecraft. The drive will engage, space will contract ahead and expand behind, and humanity will take its first step into a larger universe. Until that day, we dream, we calculate, we hope, and we rest, knowing that the future is coming. Good night, child of the cosmos. Good night, dreamer of stars. Good night, inheritor of the universe. Sleep well. The morning will bring new discoveries, and the stars will still be there, patient and beautiful, waiting for the day when we finally reach them. The warp drive is coming. The future is unfolding, and you are part of this magnificent story. Let us continue our journey a while longer, drifting through the implications of what this technology could mean, not just for exploration, but for the very nature of human civilization. When the first sailing ships crossed the Atlantic Ocean, they did not merely carry explorers and settlers. They carried ideas, they carried cultures, they carried the seeds of entirely new societies that would grow and flourish in lands far from their origins. The European age of exploration transformed the entire world, connecting continents that had been isolated for millennia, creating global trade networks, and ultimately reshaping human civilization in ways that no one could have predicted when Columbus first set sail. Warp drives would do the same on a cosmic scale. Imagine a future where interstellar travel is routine. Not easy, perhaps, not like taking a bus across town, but possible for those with sufficient resources and motivation. Ships depart Earth orbit regularly, bound for colony worlds around nearby stars. Some carry settlers seeking new homes. Some carry scientists studying alien ecosystems. Some carry entrepreneurs establishing new industries. Some carry tourists visiting the wonders of other worlds. Each of these ships carries more than people. Each carries human culture, human knowledge, human dreams. When they arrive at their destinations and establish communities there, they plant the seeds of new civilizations. These civilizations will develop their own cultures, influenced by but not identical to the societies they left behind. They will make their own discoveries, create their own art, evolve their own traditions. Over centuries and millennia, the human presence would spread across the galaxy like ripples on a pond. Each new colony would become a hub for further exploration, sending out its own ships to ever more distant destinations. The network would grow exponentially, connecting thousands and eventually millions of worlds. This is what warp drives make possible. Not just travel between stars, but the transformation of humanity from a single planet species into a galactic civilization. And with that transformation would come a kind of immortality for our species. Right now, all of humanity's eggs are in one basket. A single disaster, whether natural or self-inflicted, could end our story forever. An asteroid impact like the one that killed the dinosaurs. A supervolcano eruption that triggers global cooling. A pandemic more deadly than any we have faced. A war that escalates beyond control. A technological catastrophe we have not yet imagined. Any of these could happen. Some are actually likely over long enough timescales. The dinosaurs ruled Earth for over 150 million years before their reign was ended by a rock from space. Our species is only a few 100,000 years old. We have been lucky so far, but luck runs out. With colonies on other worlds, however, the equation changes. No single disaster could wipe out all of humanity if humanity is spread across dozens or hundreds of star systems. Our species would become effectively immortal, able to survive catastrophes that would have once meant extinction. This is one of the deepest motivations driving warp drive research. Not just curiosity about other worlds, though that matters. Not just the desire to explore, though that matters too. But the primal urge for survival, for continuity, for ensuring that the story of consciousness does not end with us. The universe is dangerous. Stars explode. Black holes consume. Galaxies collide. On the cosmic scale, destruction is constant and inevitable. But life is resilient. Life finds a way to persist, to spread, to adapt. With warp drives, human life could spread far enough and fast enough to survive anything the universe throws at it. This is the ultimate prize. This is what the mathematics of warp bubbles ultimately promises. Not just faster travel, but long-term survival. Not just reaching other stars, but ensuring that someone will always be there to reach for them. As these grand visions flow through your drowsing mind, let us return to the science, to the elegant physics that make such dreams conceivable. We spoke earlier about how the warp drive works by manipulating space-time rather than by pushing through it. But what does this really mean? How can space itself be stretched and compressed? Is space-time even a thing that can be manipulated, or is it just a mathematical abstraction? These are deep questions that touch on the nature of reality itself. In our everyday experience, space seems like nothing. It seems like emptiness, the absence of things, the void between objects. We move through space without even noticing it. It offers no resistance, no texture, no substance. It seems absurd to talk about bending or stretching something that appears to have no existence of its own. But Einstein showed us that this intuition is wrong. Space is not nothing. It is something. It has properties that can be measured. It can be affected by the presence of matter and energy. It can bend and curve and flow. It is as real as the objects we can touch and see, just more subtle and harder to detect. Think again of the trampoline analogy. The fabric of the trampoline is not nothing. It is a physical surface with real properties, elasticity and tension and mass. When you place a bowling ball on it, the fabric responds. It curves. It stretches. Other objects moving across the fabric feel this curvature, and their paths bend accordingly. Space-time is like that fabric, but in 4 dimensions instead of 2. The equations of general relativity describe precisely how space-time curves in response to matter and energy. They predict effects like gravitational lensing, where light from distant galaxies bends around massive objects closer to us. They predict gravitational time dilation, where clocks run slower in stronger gravitational fields. They predict the existence of black holes and the expansion of the universe. Every prediction has been confirmed by observation. So when physicists talk about manipulating space-time to create a warp drive, they are not engaging in pure speculation. They are working within a well-tested framework that has proven its accuracy again and again. The mathematics is solid. The physics is understood. The only question is whether we can actually produce the configurations of energy needed to create the effects described by the equations. This is an engineering question, not a physics question. The laws of physics permit warp drives. The challenge is making them work in practice. And the recent breakthroughs have shown that the engineering might be more feasible than we once thought. The key insight from the work of Jared Fuchs and his colleagues is that the warp effect does not come from expanding or contracting space in the way early theorists imagined. It comes from having large amounts of energy moving rapidly around the passenger volume. This movement creates what the researchers call a conveyor belt effect that can transport the entire bubble through space-time. Think of it like a smoke ring. When you blow a smoke ring, the air particles move in a circular pattern that creates a stable, self-sustaining structure. The ring can drift across a room, carrying its circular pattern with it. The individual air particles are not traveling across the room. They are just circling in place, but the pattern they create moves forward. A warp bubble works similarly. Energy circulates around the shell of the bubble in specific patterns. This circulation creates curvature in space-time that affects everything inside and outside the bubble. The net effect is that the bubble and everything inside it moves through space even though nothing inside the bubble is actually traveling faster than light locally. This is the loophole that makes faster than light travel possible. The speed of light limit applies to objects moving through space, but the bubble is not moving through space in the usual sense. Space is flowing around it, carrying it along, and there is no speed limit for the flow of space itself. The analogy to the expansion of the universe is exact. Distant galaxies are receding from us faster than light because the space between us is expanding. No one claims those galaxies are violating physics. They are not moving through space faster than light. Space itself is stretching, and they are being carried along by that stretch. A warp drive would create the same effect locally around a single spacecraft, in a controlled and directed manner. Instead of the random expansion of the cosmos, you would have a precisely engineered bubble of space-time manipulation, carrying its passengers to the stars. This is what the equations describe. This is what the computer models simulate. This is what the researchers are working toward. And now, with the demonstration that such effects can be achieved using only positive energy, the path forward is clearer than it has ever been. Let us talk more about what the journey itself might be like for the passengers aboard a warp-capable spacecraft. One of the most remarkable features of the Alcubierre drive and its successors is that the passengers would experience no acceleration. They would feel no crushing forces as the ship accelerated to faster than light speeds. They would float in comfortable microgravity, going about their daily activities as if nothing unusual were happening. This is because, from the perspective of physics, nothing unusual is happening inside the bubble. The interior of the warp bubble is flat space-time, undisturbed by the manipulations occurring at its boundary. Objects inside the bubble obey all the normal laws of physics. Light travels at the speed of light. Clocks tick at the normal rate. Chemical and biological processes proceed normally. The passengers would look out their windows and see the stars shift and blur as the universe outside the bubble contracted and expanded. But they themselves would feel nothing. No motion sickness, no crushing acceleration, no time dilation separating them from the rest of humanity. This last point is crucial and worth dwelling on. In conventional relativistic travel, the faster you go, the more time slows down for you relative to stationary observers. If you traveled to a nearby star at 99% of the speed of light, you might experience the journey as taking just a few months. But back on Earth, years would have passed. If you returned home, everyone you knew would have aged far more than you had. You would be a stranger from the past, displaced in time as well as space. Many science fiction stories have explored this poignant consequence of relativistic travel. The interstellar journeyer returns to find their children grown old, their friends dead, their world transformed. It is a kind of exile, permanent and irreversible. Warp drives eliminate this tragedy. Because the passengers are not actually moving through space at relativistic speeds, they experience no time dilation. Time passes for them at the same rate as for everyone else. A 6-month journey to Proxima Centauri would take 6 months for the crew and 6 months for the people waiting on Earth. Families would not be separated by decades of experienced time. Explorers could return to the same world they left. This makes interstellar travel fundamentally different in character. Instead of a one-way journey into permanent exile, it becomes a true expedition, a going forth and a returning home. The social and psychological implications are profound. Interstellar colonies would remain connected to Earth and to each other. A galactic civilization would be possible in a way that relativistic time dilation would make practically impossible. The researchers working on warp drives understand this deeply. When Harold Sonny White discusses his new nacelle geometry, he emphasizes that the interior of the bubble would have no tidal forces, 0G, and clocks synchronized with mission control. He calls it quite ideal, a nice characteristic that makes the design especially suitable for human travel. This attention to the human element is important. Warp drives are not just abstract physics puzzles. They are potential vehicles for carrying fragile biological beings across the abyss between stars. The mathematics must account for the needs of those beings, ensuring that the journey is not merely possible, but survivable and comfortable. And the latest designs do exactly that. They create stable, calm interiors where passengers could live normal lives for the duration of the voyage. They would eat and sleep, work and play, perhaps even raise children during longer journeys. The warp bubble would be their bubble of Earth-like conditions, carrying them safely through the cosmic void. Let us drift now into more speculative territory. Let us imagine some of the things that humanity might discover once warp drives open the galaxy to exploration. The most exciting possibility, of course, is finding life beyond Earth. This has been a dream of humanity for centuries, the subject of countless stories and speculations. Are we alone in the universe? Is the spark of life a rare accident, or does it kindle readily wherever conditions permit? Do other thinking beings look up at their own night skies and wonder the same questions we wonder? With warp drives, we could begin to answer these questions. We could visit the potentially habitable worlds we are discovering around nearby stars. We could analyze their atmospheres, sample their soils, and search directly for the signatures of life. Proxima Centauri b is just the beginning. Our telescopes have found thousands of exoplanets around other stars. and many of them appear to be in their stars' habitable zones. Some are rocky worlds similar in size to Earth. Some orbit calm, stable stars that might provide the billions of years needed for complex life to evolve. Any of these worlds could harbor life. Some might harbor intelligent life. Some might even harbor civilizations that have developed their own technologies and cultures. The thought of meeting other intelligent beings is both thrilling and sobering. What would we learn from creatures who evolved on different worlds under different conditions? Their biology would surely be different from ours, adapted to their unique environments. Their psychology might be different too, shaped by evolutionary pressures we cannot imagine. Their cultures, their art, their science, their philosophy, all would offer fresh perspectives on questions we have struggled with for millennia. And what would they think of us? Would they see us as kindred spirits, fellow travelers on the cosmic journey? Would they see us as threats to be guarded against, or primitives to be studied, or equals to be befriended? We cannot know until we meet them. The possibility of meeting alien intelligence raises profound questions about our own self-understanding. Right now, we have no comparison point. We know only human intelligence, human consciousness, human ways of understanding the world. We have no way of knowing whether our approach to reality is typical of thinking beings or wildly unusual. Other intelligences might think in ways completely different from our own. They might perceive dimensions of reality invisible to us. They might have solved problems we have not even recognized as problems. They might have technologies based on principles we have not discovered. Or they might not exist at all. It is possible that life is common in the universe, but intelligence is rare. It is possible that many worlds harbor microbial life, but few or none develop complex ecosystems capable of producing thinking beings. It is possible that intelligent civilizations tend to destroy themselves before achieving interstellar travel, leaving the galaxy littered with the ruins of failed species. This is one version of the answer to the Fermi paradox, the puzzle of why we have not detected any signs of alien civilizations despite the vast number of stars in the galaxy. Perhaps intelligent life is just extremely rare. Perhaps we are alone, or nearly alone, in the Milky Way. If that is the case, then the responsibility that comes with warp drives is even greater. We might be the only beings capable of spreading consciousness through the galaxy. We might be the only hope for intelligence to survive the cosmic catastrophes that will eventually occur everywhere. We might be the universe's sole chance to know itself. This is a heavy burden to contemplate, and perhaps not the best thought for drifting off to sleep. So, let us turn to lighter possibilities. Imagine the wonders we might find even on lifeless worlds. Each planet is a unique laboratory where nature has run different experiments over billions of years. The geology, the chemistry, the atmospheric dynamics of each world would offer lessons about how planets form and evolve. Imagine standing on a world with 3 suns, watching multiple shadows stretch across an alien landscape as each sun rises and sets at different times. Imagine witnessing storms larger than entire continents, driven by energies that dwarf anything on Earth. Imagine exploring caves deep beneath the surface of frozen moons, where liquid water oceans lap against rock in eternal darkness. Imagine the Pleiades rings of gas giants seen up close, not as distant photographs, but as immediate, overwhelming reality. Countless glittering particles of ice and rock circling in precise orbits, forming structures of breathtaking delicacy and grandeur. Imagine flying through the gaps in the rings, watching the ice particles drift past like snow in slow motion. Imagine the heart of stellar nurseries, vast clouds of gas and dust where new stars are being born. Young suns flickering to life amid the haze. Protoplanetary disks where worlds are just beginning to coalesce from the chaos. The raw creative power of the cosmos on display. All of this awaits us. All of this is accessible, in principle, to a civilization with warp drives. The gallery of cosmic wonders is effectively infinite, and we have been given the ticket to walk through it. As your mind relaxes further towards sleep, let us revisit the human beings who are making this possible. The researchers and engineers, the mathematicians and physicists, the dreamers who have devoted their lives to turning science fiction into science fact. Miguel Alcubierre, the young graduate student who watched Star Trek and wondered if the warp drive could be real, who could not sleep after the idea struck him, who went to his office the next day and began the calculations that would change our understanding of what is possible. His 1994 paper laid the foundation for everything that followed. Harold Sonny White, the NASA engineer who spent decades working on advanced propulsion concepts, who led the EagleWorks laboratory at Johnson Space Center, pushing the boundaries of experimental physics, who proposed refinements to the Alcubierre drive that dramatically reduced its energy requirements, who, just weeks ago, published a new design that brings the dream even closer to reality. Jared Fuchs and Christopher Helmerich, the researchers at the University of Alabama in Huntsville, who worked with applied physics to demonstrate that warp drives can use positive energy, who developed the Warp Factory software that allows anyone to model and analyze warp drive spacetimes, who changed the conversation about what is possible. Gianni Martir, the CEO of Applied Physics, who assembled a team of international scientists and engineers dedicated to making warp travel a reality, who speaks confidently of the warp age that humanity is entering, who sees the light at the end of the tunnel. These are just a few of the people involved. Behind them are hundreds of others, researchers and students and enthusiasts who contribute in ways large and small. They form a community connected by a shared dream, the dream of reaching the stars. And behind them are the giants on whose shoulders they stand. Einstein, who revealed that space-time is curved. Schwarzschild, who found the first solution to Einstein's equations describing a black hole. Wheeler, who coined the term black hole and did so much to develop our understanding of general relativity. Hawking, who showed that black holes emit radiation and eventually evaporate. And countless others whose work built the intellectual infrastructure that makes warp drive research possible. This is how science works. Each generation builds on the achievements of those who came before. Each breakthrough opens possibilities that enable further breakthroughs. The knowledge accumulates, the understanding deepens, and eventually things that once seemed impossible become routine. Flight was impossible until it was not. Space travel was impossible until it was not. Faster than light travel seems impossible now, but the mathematics is telling us that it is not impossible. It is merely very, very difficult. And humanity has never shied away from very, very difficult challenges. As the night deepens around you and sleep draws closer, let us speak of the long view. Let us consider the timescales on which these developments might unfold. The researchers working on warp drives are careful to temper expectations. They speak of decades or centuries before working prototypes might be built. They acknowledge that enormous challenges remain. They do not promise quick results. But consider what decades or centuries mean in the span of cosmic time. The universe is 13.8 billion years old. Our sun has been burning for about 4.6 billion years and will continue for another 5 billion or so. The Milky Way galaxy will exist in recognizable form for billions of years more before its eventual collision with Andromeda, reshapes it beyond recognition. On these scales, a few centuries of development time is nothing, a blink of an eye. If humanity achieves working warp drives in the year 2300 or 2500 or even 3000, we will still be incredibly early to the cosmic party. We will have billions of years ahead of us to explore and expand. This long view provides a kind of comfort. We do not need to solve all the problems today. We do not need to rush. The universe will wait. The stars are not going anywhere. What matters is that we keep working, that we maintain the momentum of research and development, that we pass the torch from generation to generation, each cohort building on what came before. If we do this, the warp drive will come, not because of any magic or miracle, but because of sustained effort applied over time to a problem that physics tells us has a solution. This is the nature of scientific progress. It is slow when viewed up close, marked by frustrations and dead ends and incremental advances. But viewed from a distance, viewed across decades and centuries, it is astonishingly fast. The entire history of modern physics, from Newton to the present, spans only about 350 years. In that time, we have gone from not understanding why apples fall to precisely modeling the curvature of spacetime around black holes. Give us another 350 years or another 1,000, and what might we achieve? The warp drive researchers are playing a long game. They are laying foundations for a technology that may not be completed in their lifetimes. They are accepting that they are part of a larger project, one that transcends individual careers and lifespans. They are working for a future they may never see. This is a noble form of human endeavor. It connects us to both past and future, making us links in a chain that stretches across generations. The scientists of today honor the scientists of yesterday by building on their work. The scientists of tomorrow will honor us by building on ours. The chain continues, and with each link, our reach extends further into the cosmos. Sleep now, knowing that the work continues, that even as you rest, someone somewhere is pondering an equation, running a simulation, writing a paper that will advance our understanding. The collective human mind never sleeps entirely. Around the world, around the clock, the project of exploration and discovery goes on. You are part of this project simply by being aware of it, by understanding what is being attempted, by hoping for its success. The dream of the stars is a shared dream, belonging to everyone who has ever looked up at the night sky and wondered. And that dream is closer to reality tonight than it has ever been. The cosmos is patient, but it is also generous. It has given us minds capable of comprehending its structure. It has given us hands capable of building instruments to probe its secrets. It has given us time, billions of years of cosmic time, to figure out how to explore its expanse. And now it has given us the mathematics of warp drives. The equations that say faster than light travel is possible. The models that show how it might be achieved. The hope that our descendants will walk on worlds orbiting other stars. What more could we ask? Rest now, inheritor of stars. Rest now, child of an awakening cosmos. The night is deep and the universe is vast, but you are not alone in either. Billions of humans share this earth with you, each one a spark of consciousness flickering in the cosmic dark. Billions of stars shine in the galaxy around us, each one a potential destination, a potential home. And somewhere in the mathematics of spacetime, somewhere in the elegant curves of Einstein's equations, the path to those stars lies waiting to be walked. We will walk it. Perhaps not today, perhaps not tomorrow, but someday. The warp drive will be built. The first interstellar voyages will Be made. The human presence will spread across the galaxy. This is not wishful thinking. This is not unfounded optimism. This is the logical conclusion of what the physics tells us and what the recent breakthroughs have demonstrated. The speed of light is not a prison wall. It is a doorway, and we are learning to open it. Good night, fellow traveler. May your dreams carry you to the stars that await. May your sleep be deep and restful, renewing you for whatever challenges tomorrow brings. And may you wake knowing that the universe is more wonderful, more accessible, more full of possibility than you dared to imagine. The warp drive is coming. The future is unfolding. The stars are calling. And one day, not so very long from now, in cosmic terms, we will answer. Sleep well. As consciousness fades and dreams begin to take shape, carry with you one final thought, one final image to accompany you into the night. Imagine a future astronaut standing in the observation deck of a warp-capable spacecraft. Behind them, Earth has shrunk to a blue dot, then vanished into the glare of the sun. Around them, the stars that seem fixed, points their entire life have begun to shift, sliding slowly across the view screen as the ship accelerates toward its destination. The astronaut is not afraid. They know that inside this bubble of warp space-time, they are as safe as they would be in their bedroom back home. They know that the physics works, that the engineers have done their job, that the mathematics, discovered over a century ago, has been translated into reliable technology. They think of all the people who made this moment possible, the dreamers and the calculators, the theorists and the engineers, the generations of scientists who each contributed a piece to the puzzle until the picture was complete. They think of Alcubierre, watching Star Trek in a dormitory in Wales. They think of White, running experiments in his NASA laboratory. They think of Fuchs, developing software to model the impossible. They think of all the unnamed researchers who filled in the gaps, who checked the equations, who kept the dream alive. And they think of you, yes you, listening to these words so long ago, drifting off to sleep with thoughts of warp drives and distant stars filling your mind. You, who lived in the time when this was still a dream. You, who hoped and wondered and believed that someday it would come true. The astronaut smiles. They know that they are not alone in this vast cosmos. They carry with them the hopes and dreams of everyone who ever looked up at the night sky and felt the call of the stars. The warp drive hums softly as it does its work, bending space and time around the ship. The stars continue their slow drift, and the astronaut, this future inheritor of your dreams, settles in for the journey ahead. They are going to see another world. They are going to touch the soil of a planet that circles a distant sun. They are going to add another chapter to the story of life and intelligence in the universe. And it all started here, with equations written on paper, with theories proposed and tested, with dreams nurtured across generations, with people like you imagining what might be possible. Thank you for dreaming with us tonight. Thank you for caring about the future of humanity among the stars. Thank you for being part of the great project of consciousness exploring itself. The universe is vast and ancient and beautiful beyond measure, and you belong to it. You are made of it. You are it looking at itself, wondering about itself, dreaming of spreading across itself. What a magnificent thing to be. What a remarkable time to exist. What a gift to be aware of the cosmic story and to know that it is not over, that the best chapters may still be ahead. Sleep now, stargazer. Sleep now, cosmic dreamer. Sleep now and know that the future is bright with possibility. The warp drive is coming. The stars are waiting. And the journey The great journey of humanity into the galaxy has only just begun. But before sleep claims you entirely, let us wander a while longer through the garden of cosmic possibilities. There is so much more to explore, so many more wonders to contemplate. We have spoken of distant stars and alien worlds, but we have not yet fully explored what lies within our own stellar neighborhood. The solar region within 100 light-years of Earth contains thousands of stars, many with their own planetary systems. Even with current observation technology, we have begun to catalogue some of these worlds. Within this relatively small sphere of space, we have found a remarkable diversity of planetary systems. Some stars are orbited by giant planets larger than Jupiter, massive balls of gas and storms that dwarf anything in our own solar system. Others host small, rocky worlds, some in the habitable zones where liquid water might pool on the surface. A few systems are packed with multiple planets, their orbits nested together in complex gravitational dances. Others are sparse, with just one or two worlds circling in isolation. Each of these systems is a potential destination for a warp-capable spacecraft. Each could be reached in weeks or months rather than millennia, and each holds its own mysteries waiting to be explored. Consider the star Tau Ceti, about 12 light-years from Earth. It is a G-type star similar to our Sun, slightly smaller and cooler, but fundamentally the same kind of stellar engine. Astronomers have detected at least 4 planets orbiting Tau Ceti, and possibly as many as 8. Some of these worlds may be in the habitable zone. At 10 times the speed of light, Tau Ceti is just over a year away. A mission could launch, travel to the star, spend months exploring its planetary system, and return to Earth within 3 or 4 years. Scientists who planned the mission could expect to see its results. Families would not be separated for generations. Or consider Epsilon Eridani, about 10.5 light-years distant. This is a young star, only about 800 million years old compared to our Sun's 4.5 billion years. It has at least one confirmed planet, a gas giant several times the mass of Jupiter. But around young stars like this, we might find worlds in the early stages of planetary evolution, their surfaces still raw and chaotic, their atmospheres still forming from the gases released by volcanic eruptions. To witness a young planetary system would be to look back in time in a sense. We would see conditions similar to what existed in our own solar system billions of years ago. We would learn about how planets form and mature. We would understand our own origins better by comparing them to other systems at different stages of development. The nearby stellar neighborhood also contains several red dwarf stars, cool, dim suns that burn their hydrogen fuel slowly and live for trillions of years. Proxima Centauri is one of these. Others include Barnard's star, about 6 light-years away, and Wolf 359, about 7.9 light-years distant. Red dwarfs are the most common type of star in the galaxy. If planets orbiting red dwarfs can support life, then the galaxy is far richer in potentially habitable worlds than we once thought. But red dwarf planets face challenges that planets orbiting sun-like stars do not. Red dwarfs are dim, so the habitable zone is very close to the star. Planets in this zone may be tidally locked, with one side always facing the star and one side in perpetual darkness. Red dwarfs are also prone to powerful flares that could strip away atmospheres and sterilize surfaces. Studying red dwarf planetary systems up close would help us understand whether life can exist around these common stars. It would expand or constrain our estimates of how much life there might be in the galaxy, and it would provide crucial information for any future efforts to colonize worlds around red dwarfs. These are just a few examples from our immediate stellar neighborhood. Extend the radius to 1,000 light years, still a tiny fraction of the galaxy, and the number of potential destinations grows into the millions. Extend it to the entire Milky Way, and we are talking about hundreds of billions of star systems, each one unique, each one holding its own secrets. This is the true scale of what warp drives would open up. Not just a few destinations, but an effectively unlimited frontier. More worlds than humanity could fully explore in millions of years of effort. More diversity than our wildest imaginations could encompass. The cosmos is generous beyond measure. It has provided more wonders than we could ever exhaust. All we need is the ability to reach them. And now, thanks to the work of physicists and engineers around the world, we know that ability is not forbidden by nature. It is merely waiting to be developed. Let us turn our attention now to some of the technical details that might shape the design of future warp-capable spacecraft. These considerations are speculative, since no one has yet built such a vehicle, but they follow logically from what we know about warp physics. First, the question of size. How large would a warp bubble need to be to contain a spacecraft and its crew? The answer depends on several factors. Larger bubbles require more energy to maintain, so there is pressure to keep them as small as practical. But the bubble must be large enough to contain everything needed for the voyage, including the crew quarters, life support systems, fuel, cargo, and the warp drive machinery itself. Current models suggest that the energy required scales with the surface area of the bubble rather than its volume. This means that larger bubbles are relatively more efficient in terms of energy per unit of interior space. A bubble 10 meters across might take nearly as much energy to maintain as a bubble 50 meters across, but the larger bubble would have 125 times more interior volume. This favors designs with substantial interior space. Future warp ships might be relatively roomy compared to the cramped spacecraft of today. They might have separate compartments for work and recreation, individual sleeping quarters, exercise facilities, and observation decks with large windows looking out at the warped starfield. Of course, the energy requirements are still enormous by current standards. But if those requirements can be met at all, economies of scale might favor larger ships over smaller ones. Second, the question of navigation. How do you steer a warp bubble? Inside the bubble, the local spacetime is flat and normal, but the bubble is embedded in warped spacetime, moving through a universe that appears distorted from the outside. Light from external sources would be shifted and bent as it passed through the boundary of the bubble. Communication with the outside universe would be difficult or impossible while the warp drive is engaged. This presents a navigation challenge. How do you know where you are if you cannot see the stars clearly? How do you correct your course if you drift off target? One solution might be to rely on precise calculations before engaging the warp drive. You would determine your starting position and velocity very precisely. Calculate the trajectory needed to reach your destination. Program the warp drive to create exactly the space-time distortion required, and then trust the mathematics. Upon arrival, you would drop out of warp and verify your position using conventional methods. This approach requires extremely accurate calculations. Even small errors could compound over light years of travel, leaving you far from your intended destination. But mathematics is something humans are good at, and computers are even better. With sufficient care and precision, this kind of dead reckoning navigation might be feasible. Another solution might involve periodic pauses to check your position. The warp drive could be cycled on and off, allowing brief windows during which normal space travel and observation are possible. These pauses would add time to the journey, but would provide opportunities to verify course and make corrections. A third possibility involves developing new technologies that can function within the warped space-time of the bubble boundary. Perhaps sensors could be designed that account for the distortion, extracting useful information from the bent light and shifted signals. This would require a deep understanding of how the bubble interacts with electromagnetic radiation, an understanding that is still being developed. Whatever the solution, navigation is a challenge that must be addressed before practical warp travel becomes possible. The researchers working on warp drives are aware of this, and future work will likely focus on these operational questions as well as the fundamental physics. Third, the question of safety. What happens if something goes wrong during a warp voyage? The warp bubble is maintained by specific configurations of energy circulating around its boundary. If that circulation is disrupted, if the energy flows become unstable or dissipate, the bubble would collapse. What happens to the ship and crew inside a collapsing warp bubble? This is not fully understood. The mathematics becomes extremely complex in such scenarios, and current models may not capture all the relevant physics. It is possible that a controlled collapse would simply drop the ship back into normal space, perhaps with some residual velocity. It is also possible that a sudden collapse could subject the ship to intense gravitational forces or other hazards. Understanding these failure modes is crucial for designing safe warp drives. Engineers will need to develop systems that can maintain bubble stability under a wide range of conditions. They will need backup systems that can safely shut down the drive if problems occur. They will need procedures for emergency situations, analogous to the abort modes that space missions use today. All of this work lies ahead. The current focus is on demonstrating that warp drives are possible at all. Once that is established, attention will shift to these practical engineering concerns. Safety will be paramount, just as it is in aviation and current space travel. Fourth, the question of fuel. What provides the energy for a warp drive, and how much is needed for a given journey? As we have discussed, current models require energy equivalent to planetary masses. This is far beyond what any existing power source can provide. But let us assume that future technology finds ways to generate and handle such energies. What would the fuel requirements look like? If antimatter turns out to be the fuel of choice, a warp ship might carry tanks of stored antiparticles, carefully contained in magnetic bottles that prevent them from touching normal matter. Upon engaging the warp drive, controlled amounts of antimatter would be allowed to annihilate with matter, releasing tremendous energy that would be channeled into the space-time manipulation systems. The efficiency of this process would determine how much antimatter is needed for a given journey. With perfect efficiency, a journey to Proxima Centauri might require a few hundred kilograms of antimatter, a feasible amount to carry if we ever learn to produce antimatter in quantity. With lower efficiency, the requirements could be much higher. Other potential fuel sources are even more speculative. Some researchers have suggested harnessing vacuum energy, the quantum fluctuations that permeate all of space. Others have proposed using exotic physics like negative energy states or dark matter interactions. These ideas are still highly theoretical, but they represent possibilities that future generations might explore. The fuel question is intimately linked to the energy requirement question. Any reduction in the energy needed for warp travel directly reduces the fuel needed. This is why the recent breakthroughs are so significant. By showing that positive energy can create warp effects, and by demonstrating that the energy requirements depend on the bubble's shape, the researchers have opened the door to more efficient designs that might eventually make warp travel practical. Fifth, the question of crew and cargo. What would be transported on warp voyages, and who would make the journeys? Early warp ships would likely carry small crews of highly trained specialists, pilots and engineers to operate the vessel, scientists to conduct observations and experiments, technicians to maintain the complex systems, perhaps a few dozen people in total, carefully selected for their skills and psychological suitability. As the technology matured and costs declined, larger ships might carry more diverse passengers. Colonists bound for new worlds, tourists visiting cosmic attractions, business travelers conducting interstellar commerce. The diversity of space travel would come to mirror the diversity of terrestrial travel today. Cargo would also be transported. Raw materials from resource-rich worlds, manufactured goods from industrial colonies, scientific samples for analysis on Earth, cultural artifacts exchanged between human communities spread across the stars. Information, of course, could be transmitted at light speed and would not need physical transport, but physical goods would require ships. A mature interstellar economy might see fleets of warp-capable freighters moving between star systems, their schedules and routes optimized for efficiency. Space stations and orbital facilities would serve as hubs, where ships from many origins could exchange cargo and passengers. The logistics would be complex but manageable with advanced computing and careful planning. This vision of interstellar commerce lies far in the future, but it is the logical endpoint of warp drive development. Technology that begins as a scientific curiosity eventually becomes infrastructure that supports civilization. Airplanes were once experimental novelties. Now they carry billions of passengers each year. Warp drives could follow the same trajectory, transforming from laboratory demonstrations to reliable transportation over the course of centuries. As these practical considerations drift through your settling mind, let us return once more to the poetry of the cosmos. Let us remember why any of this matters beyond the engineering and the physics. Humanity needs frontiers, not just to survive, though survival matters, not just to prosper, though prosperity matters too. We need frontiers because we are a species of explorers, because our spirits wither when confined to too small a space. Consider the great ages of exploration in human history. The Polynesian navigators who crossed vast stretches of Pacific Ocean in outrigger canoes, settling islands scattered across a quarter of the planet. The Chinese fleets of Zheng He, reaching Africa and the Middle East in voyages of trade and diplomacy. The European age of sail, which mapped the coastlines of every continent and established the first truly global civilization. These explorations were difficult and dangerous. Many people died. The societies that emerged were imperfect, often tragically so. But something valuable also emerged, a sense of possibility, a belief that there is always more to discover, that the horizon can always be reached and crossed. We lost that frontier when we completed the map of Earth. There are no more unknown continents to discover, no more blank spaces that might contain wonders. We have been everywhere on our planet. We have seen it all. But space remains unexplored. The stars still beckon, and with warp drives, we could answer their call. The psychological and spiritual benefits of having a frontier should not be underestimated. A civilization with somewhere to go, with challenges to overcome and wonders to discover, is a civilization with purpose. A civilization confined to a single world, with no new horizons, risks stagnation and despair. The dream of the stars has sustained many people through difficult times. The knowledge that human destiny lies beyond this one planet, that the universe awaits our exploration, provides hope that transcends immediate circumstances. Even before warp drives were shown to be possible, even when interstellar travel seemed impossibly remote, the dream itself had value. Now that dream is more substantial. Now it rests on a foundation of physics and mathematics, not just imagination. The warp drive researchers have given us something precious, the knowledge that our species is not trapped here, that the cage we thought we were in has a door, that the stars are truly within reach. This knowledge changes everything, even if the actual journeys lie centuries in the future. It reframes our sense of what humanity is and what it might become. It connects us to a future that is grander than any we previously imagined. It gives meaning and direction to the scientific enterprise as a whole. And it offers each of us tonight a reason to look up at the stars with renewed wonder and hope. The light you see from those distant suns has traveled for years to reach your eyes. But the distance that light has crossed is not a permanent barrier. It is merely a challenge that brilliant people are working to overcome, a challenge that will eventually be met. You are alive at the threshold of a new age, the age of interstellar humanity, the age when our species finally claims its inheritance among the stars. What a time to be conscious. What a gift to witness this moment. Sleep now, with visions of warp bubbles and starships dancing in your dreams. Sleep with the knowledge that the future is brighter than you knew. Sleep knowing that the work continues, that the progress is real, that the destination grows closer with each passing year. The cosmos has waited billions of years for beings capable of exploring it. It can wait a while longer, but it will not have to wait forever. The warp drive is coming, the ships will be built, the voyages will be made, and humanity will finally go home to the stars from which it came. Rest, now, in the cradle of your bed, on the surface of this blue world, in the arms of this galaxy, within the vast embrace of an awakening universe. You are not alone. You are never alone. You are part of everything, connected to everything, made of everything, and everything is waiting to be explored. Good night, gentle soul. May your dreams be peaceful and your sleep be deep. The stars will be there when you wake. They always are. And thanks to the work being done right now, they are closer than they have ever been. Sleep well, dream well, and know that the future is full of wonder. But let us linger just a little while longer in this space between waking and sleeping. There are a few more thoughts to share, a few more connections to make before we bid final farewell to this evening's contemplation. We have spoken much about the physics of warp drives, about the mathematics and the engineering challenges, but we have not fully explored what these discoveries mean for our understanding of reality itself. For centuries, scientists believed that space-time was a fixed stage on which the drama of the universe played out. Matter and energy moved across this stage, interacting according to physical laws, but the stage itself was immutable. It provided the backdrop but did not participate in the action. Einstein changed this understanding. He showed us that space-time is not a stage, but an actor. It responds to matter and energy. It bends and curves. It participates in the dynamics of the cosmos. Space-time is not nothing, it is something, and that something can be manipulated. The warp drive represents the logical conclusion of this insight. If space-time can be curved by mass and energy, then perhaps it can be shaped for our purposes. Perhaps we can learn to sculpt space-time the way we sculpt stone or metal. Perhaps the fabric of reality itself can become a medium for human creativity and engineering. This is a profound shift in perspective, We are used to thinking of ourselves as small, passive observers in a vast and indifferent cosmos. We witness the universe but do not shape it. We are carried along by cosmic forces far beyond our control. But if we can manipulate space-time, if we can create warp bubbles that carry us across the galaxy, then we become active participants in the cosmic drama. We become shapers of reality, not merely observers of it. The universe is no longer something that happens to us. It becomes something we happen to. This transformation has been happening gradually throughout human history. We learn to shape stone into tools. We learn to shape plants and animals through domestication. We learn to shape matter through chemistry and materials science. We learn to shape energy through electricity and nuclear power. And now, we are learning to shape space-time itself. Each step in this progression has expanded our capabilities and our reach. Stone tools let us hunt more effectively and spread across the planet. Agriculture let us build cities and civilizations. Chemistry let us create new materials with properties tailored to our needs. Electricity lit our nights and powered our industries. Nuclear energy, for all its dangers, provided a concentrated source of power unlike anything before. Space-time engineering would be the next step, and perhaps the greatest. It would give us access to the entire galaxy, eventually perhaps the entire universe. It would free us from the constraints of distance that have limited every previous civilization. It would open possibilities that we can barely imagine from our current vantage point. The researchers working on warp drives understand the magnitude of what they are attempting. They know that success would change the trajectory of human history more profoundly than any previous technology. They approach their work with appropriate humility and awe, but they also approach it with determination. The mathematics is encouraging. The physics is permissive. The engineering challenges, while enormous, are not insurmountable. There is no fundamental reason why warp drives cannot be built. It is simply a matter of time, resources, and sustained effort. And so they continue their work. Day after day, year after year, they push the boundaries of human knowledge. They solve equations that no one has solved before. They model space-time configurations that have never been studied. They lay the intellectual foundations for a technology that will transform our species. This is noble work. This is important work. And it deserves our attention and support. As you drift towards sleep, consider what you might do to support this grand project. Perhaps you are a scientist yourself, or could become one. Perhaps you are an engineer who could contribute technical skills. Perhaps you are an educator who could inspire the next generation of space dreamers. Perhaps you are a citizen who could advocate for funding and resources for space research. Even simply understanding and appreciating this work has value. Every person who knows about warp drives, who hopes for their success, who shares the dream of interstellar humanity, adds to the collective will that drives progress forward. Civilizations accomplish great things when their members share a vision of what is possible. Your awareness of this vision matters. The children being born today may live to see the first warp experiments. Their children may witness the first interstellar voyages. The timeline is uncertain, but it is not impossibly long. Within a few generations, everything we have discussed tonight could become reality. What a legacy that would be. What a gift from our generation to our descendants. The gift of the stars. Let us also take a moment to appreciate the interconnection between scientific fields that makes warp drive research possible. The warp drive researchers draw on general relativity, a theory developed in the early 20th century to explain gravity. They use computational methods that depend on advances in mathematics and computer science over the past several decades. They benefit from experimental techniques developed by particle physicists and astronomers. They are informed by cosmological observations that have revealed the nature of the expanding universe. No single scientist could have developed warp drive theory alone. It required generations of accumulated knowledge, each building on what came before. Newton developed the mathematics of calculus that Einstein would later use. Riemann developed the geometry of curved spaces that general relativity employs. Minkowski recognized that space and time form a unified four-dimensional structure. And beyond the scientists, there are the engineers and technicians who build the instruments, the administrators who manage the institutions, the taxpayers who fund the research, the teachers who educate new generations of scientists. The whole edifice of modern science is a collaborative enterprise involving millions of people across centuries. When a warp drive eventually flies, it will be the product of this vast cooperative effort. It will embody the contributions of countless individuals, most of whose names will never be remembered. But their work will live on in the capability they created, in the ships that cross the galaxy, in the civilizations that flourish on distant worlds. This is the beauty of human civilization at its best. We build on each other's achievements. We pass knowledge from generation to generation. We accomplish together what none of us could accomplish alone. The warp drive is perhaps the ultimate expression of this collective genius. It will be the culmination of centuries of scientific progress, the application of our deepest understanding of reality to the practical problem of crossing the void between stars. And it will be just the beginning. Once we have warp drives, we will discover new phenomena, encounter new challenges, develop new technologies to address them. The process of discovery and innovation will continue indefinitely into the future. There is no endpoint to this journey. There is no final destination at which we will arrive and declare that exploration is complete. The universe is probably infinite, and even if it is not, it is far larger than humanity could ever fully explore. There will always be more to discover, more to understand, more to wonder at. This is reassuring in its way. It means that the adventure will never end. It means that future generations will have their own frontiers to explore, their own challenges to overcome, their own contributions to make. We are not the end of history, but merely one chapter in an ongoing story. Let this thought accompany you into sleep. You are part of an epic narrative that stretches across billions of years and extends indefinitely into the future. Your moment is brief by cosmic standards, but it is precious. You are here now, aware of the universe and your place in it. That awareness connects you to everything that has been and everything that will be. The atoms in your body have traveled through stars and space over billions of years to assemble into you. One day, they will disperse and become part of something else. But for now, they form a pattern that can think and feel and dream. They form a window through which the universe experiences itself. What a magnificent thing you are. What a remarkable accident of cosmic history. What a gift to be, conscious, to wonder, to hope. As your consciousness dims towards sleep, let go of any anxieties or worries that might trouble you. The universe is vast and mostly empty, but it is not hostile. It is simply indifferent, and indifference can be a form of acceptance. The cosmos does not judge you or condemn you. It simply contains you, as it contains everything else, part of the great tapestry of existence. And within that tapestry, remarkable things are possible. Stars are born and die. Galaxies spiral through eons. Life arises on countless worlds. Intelligence emerges and begins to understand its own nature. And sometimes, when conditions are right and determination is strong, intelligence finds ways to reach across the vast distances that separate the islands of matter in the cosmic ocean. We are in the early stages of that reaching. The first tentative steps have been taken. The mathematics has been worked out. The path is becoming visible through the fog of the future. One day, perhaps sooner than anyone expects, a warp bubble will form. Space will contract ahead and expand behind, and a ship carrying human beings will begin the first interstellar journey in history. The passengers will not feel the motion. They will float in comfortable microgravity, chatting, working, gazing out at the warped starfield. But they will know that something momentous is happening. They will know that they are pioneers, the first of their kind to venture beyond the solar system that birthed humanity. They will think of everyone who made their journey possible, the scientists and engineers, the dreamers and calculators, the generations of human beings who looked up at the stars and wondered if they could ever be reached. And perhaps, in that moment, they will think of nights like this one. Quiet nights when people lay in their beds and imagined the future. Nights when the dream of the stars provided comfort and hope. Nights when the vast distances between suns seemed a little less intimidating, a little more like challenges waiting to be overcome. You are having one of those nights right now, and in some small way, you are contributing to that future. By dreaming it, by believing in it, by holding space in your consciousness for the possibility of interstellar humanity. Dreams matter. They shape what we strive for and what we achieve. A civilization that dreams of the stars will eventually reach them. A civilization that dreams only of the ground will remain bound to it. So dream boldly, tonight. Dream of warp bubbles and starships. Dream of alien sunsets and unfamiliar constellations. Dream of human footprints on worlds circling distant suns. Dream of the future that the warp drive researchers are working to create. And know that those dreams are not fantasy. They are grounded in physics and mathematics. They are supported by real research being done by real scientists. They represent a future that is possible, achievable, and perhaps closer than anyone realizes. The universe is full of wonders, and thanks to the work being done right now, we are learning how to reach them. This is the message of the warp drive research. This is what the breakthroughs of recent months and years have given us. Not just equations and papers, but hope. Not just theories, but a path forward. Not just dreams, but the beginnings of a plan to make those dreams real. The stars are calling, and at last we know how to answer. Rest now, cosmic voyager. Rest now, dreamer of infinite spaces. The night is deep and the universe is vast, but you are exactly where you need to be. Tomorrow will bring its own concerns and challenges, but tonight you can set all of that aside. Tonight you can simply rest in the knowledge that the future is unfolding beautifully, that brilliant minds are working on remarkable problems, that humanity is taking steps toward its cosmic destiny. The warp drive is coming. The engineering challenges are being addressed. The mathematics is being refined. The path to the stars is becoming clearer with each passing year. And you, tonight, are part of the generation that witnessed this becoming. You are alive at the threshold of a new era. You have seen the impossible become possible. What a gift. What a remarkable time to exist. Sleep now, and let these thoughts settle into your subconscious. Let them become part of how you understand the world and your place in it. Let them give you hope for the future and wonder at the present. The cosmos cradles you in its vast embrace. The stars shine their ancient light down upon you. And somewhere, in the quiet of a laboratory or the glow of a computer screen, scientists are working on the equations that will one day carry your descendants to those stars. Rest well, knowing this. Dream deeply, imagining it, and wake tomorrow with renewed appreciation for the magnificent universe you inhabit. The warp drive awaits, the future beckons, and the greatest adventure in human history is just beginning. Good night, traveler. Good night, dreamer. Good night, child of the stars. May your sleep be peaceful and your dreams be bright with possibility. The universe loves you. It made you from its substance. It gave you consciousness to appreciate its wonders. And now it is revealing the secrets that will let you explore its expanse. What more could any of us ask? Sleep well. As the last traces of wakefulness dissolve into the peace of slumber, let us share one more journey, one final voyage through the cosmos before dreams claim you entirely. Close your eyes now, if they are not already closed. Feel the weight of your body sinking into the mattress. Feel the rhythm of your breath, slow and steady. Feel the beating of your heart, that faithful engine that has kept you alive since before you were born. Now imagine that your awareness is expanding, floating upward from your body, through the ceiling, through the roof, into the night sky above. You can see your neighborhood spread out below you, the lights of homes where other people are settling into sleep. You can see the roads and the parks, the familiar geography of your daily life growing smaller as you rise. Higher now, the city becomes a cluster of lights against the dark land. Rivers and lakes catch the moonlight. The coastline, if there is one near you, curves away into the distance. You are seeing Earth as few humans ever have from high above. Higher still, the curvature of the planet becomes visible. The thin blue line of atmosphere, that fragile envelope of air that makes all life possible, glows faintly against the blackness of space. Clouds swirl in great patterns across oceans and continents. You can see the Terminator, the line between day and night, creeping slowly across the surface as Earth rotates. You are in space now, looking back at the world that made you. So beautiful, so small, so precious. Turn around, look outward. The moon hangs nearby, its cratered face illuminated by sunlight. Beyond it, the other planets of the solar system trace their patient orbits. Mars, rusty red. Jupiter, massive and striped. Saturn, ringed in glory. The outer planets, dim and cold in the distant darkness. And beyond them, the stars. Thousands of stars visible to your naked eye, millions more too faint to see without instruments. Each one a sun like ours. Each one potentially orbited by worlds of its own. You know now that these stars are not unreachable. You know that the mathematics of spacetime allows for faster than light travel. You know that scientists are working even as you sleep to make interstellar voyages possible. Imagine reaching out toward those stars. Imagine a warp bubble forming around you, a shell of warped space-time that will carry you across the light years. Imagine space contracting ahead of you, the stars rushing closer, the impossible distances shrinking to something manageable. You are moving now, in your imagination, faster than light. The stars slide past like streetlights seen from a speeding car. The constellations distort and reform as your perspective shifts. You are traveling farther than any human has ever traveled, farther than any probe we have ever launched. Ahead, a star grows brighter. Proxima Centauri, that nearest of stellar neighbors. You are approaching it now, slowing, the warp bubble dissipating as you arrive. And there, orbiting this alien sun, a world awaits. Proxima Centauri b, a planet that might be Earth-like, a world that might harbor life. You descend through its atmosphere if it has one, touching down on soil that no human has ever touched. You look up at a sky lit by a red sun, at stars arranged in unfamiliar patterns. You have done it. You have reached another star. This journey is imaginary tonight, but one day, perhaps not so very far from now, it will be real. Real ships will make real voyages. Real humans will stand on real alien worlds and look up at real alien skies. And it will all have begun with nights like this one. Nights when people dreamed of the stars. Nights when physicists puzzled over equations. Nights when the impossible slowly became possible through the patient accumulation of knowledge and the bold application of imagination. You are part of this story. Your dreams tonight are threads in the tapestry of human aspiration that will eventually weave itself into the reality of interstellar civilization. Return now gently to your body. Feel yourself settling back into the comfortable weight of physical existence. Feel the bed beneath you, the blankets around you, the pillow cradling your head. You are safe. You are warm. You are exactly where you need to be. The stars will wait for you. They have waited billions of years already. They can wait a little longer while you rest and renew yourself for whatever tomorrow brings. But know that they are calling. Know that the void between them is not as impassable as it once seemed. Know that the warp drive is coming, that the future is unfolding, that humanity's destiny among the stars is slowly taking shape. The researchers in their laboratories, the engineers at their computers, the students in their classrooms, learning the physics that will one day carry ships across the galaxy. All of them are working, consciously or not, toward the same goal. All of them are building the bridge that will connect Earth to the cosmos. And you, tonight, are dreaming that bridge into existence. You are holding space in human consciousness for the possibility of interstellar travel. You are contributing, in your own way, to the collective vision that drives progress forward. Thank you for dreaming with us. Thank you for caring about the future of humanity among the stars. Thank you for taking this journey through the night, exploring the science and the wonder of warp drives and faster than light travel. The universe is vast and beautiful and full of mysteries waiting to be solved. The stars are distant but not unreachable. The future is uncertain but bright with possibility. Rest now in that brightness. Sleep peacefully in the knowledge that tomorrow will bring new discoveries, new advances, new steps toward the cosmic destiny that awaits our species. The warp drive is coming. The ships will be built. The voyages will be made. And one day, human beings will walk on worlds circling distant suns, looking back at Earth as a tiny point of light, remembering the planet that gave them birth and the dreamers who made their journey possible. May you live to see that day. May your children or your children's children be among those who make the journey. May the dream we have shared tonight become the reality of generations to come. Until then, rest well, dream deeply, and know that the stars are waiting, patient and beautiful, ready to welcome humanity home. Good night, fellow traveler. Good night, cosmic dreamer. Good night, inheritor of the universe. The night is peaceful, the stars are bright, and the future has never looked more promising. Sleep now. Good night.